Chapter 25 Electromagnetic Waves. Here is the overview of Chapter 25. We will first talk about the production of electromagnetic waves. Then we will talk about how the electromagnetic waves propagate. Then we will move on to the electromagnetic spectrum and talk about all the different types of electromagnetic waves there are. Finally, we will move on to the energy and momentum in electromagnetic waves, and to finish, we will talk about the polarization of electromagnetic waves. Electromagnetic waves can be produced by oscillating charges. Here we have an example where an AC circuit, AC being short for alternating current, produces such oscillating charges and creates an electromagnetic wave. We start off with the situation where the negative charge is on the bottom and there's some positive charge on the top. This creates an electric field vector that points in the downwards direction. Then, as the time increases, we find that we have less negative charge on the bottom and less positive charge on the top. We still have an electric field vector that points in the downwards direction, but it's reduced in size as a result. We then move to a situation where we have no positive or negative charge on the bottom, and this gives us a zero electric field vector. Then things proceed in a way where the negative charge is now on the top and the positive charge on the bottom, and this switches the electric field to point in the upwards direction. We then get more negative charge on the top and more positive charge on the bottom, and this leads to a greater electric field that points in the upwards direction. The negative charge on the top and positive charge on the bottom then starts to reduce, the electric field vector reduces, and we then arrive back to the point where there is no electric field vector because there is no excess charge on the top or the bottom. The process can then repeat itself where one could then build more negative charge on the bottom and positive charge on the top. The wave created in this process will move to the right as time goes on. Now, the previous slide shows how the electric field is produced. As we learned in Chapter 22, charges that move in the form of a current also produce a magnetic field. And it turns out that in the previous slide, a magnetic field vector will also be produced by the oscillating charge. This will be perpendicular to the electric field direction and perpendicular to the direction of propagation of the wave. When we produce any electric field from an antenna that's connected to an AC generator, this will always propagate away from the antenna. Here we have an electromagnetic wave propagating in the x direction. By propagating, we mean that the peaks of the wave and the minima of the wave will move in the x direction. We can see that the electric field points in the z direction and the magnetic field points in the y direction. We can also see that the electric and magnetic fields are in phase. By that, we mean that the peak of the electric field will occur at the same x position as the peak of the magnetic field. The same applies to the minima. The direction of propagation and the directions of the electric and magnetic fields can be determined using a right-hand rule. In doing so, the index finger will represent the wave direction, the thumb the magnetic field direction, and the middle finger will represent the electric field direction. For any oscillation to occur, there has to be an acceleration that continues to change the motion of the thing that is oscillating. It turns out that for any electric charge that is accelerated, there will be an electromagnetic wave. We have an example on the bottom where the maximum of the radiation will be perpendicular to the movement of the current, and the minimum of the radiation will be parallel to the direction of the current. Essentially, where there is zero radiation, the charge does not appear to be oscillating, it appears to be in the same place, and that's why there is zero radiation. When one is perpendicular, the oscillation appears maximum. All electromagnetic waves propagate through a vacuum with the exact same speed. That speed we refer to as the speed of light in a vacuum, and it is 3 by 10 to the 8 meters per second. When electromagnetic waves pass through other materials such as air and water, this speed slows down, and it can slow down by up to half the speed in a vacuum. We can calculate the speed of light using electromagnetic theory, and it turns out that this will equal 1 over the square root of epsilon naught times mu naught. That gives a speed in meters per second, which translates to about 670 million miles per hour. So this is a very, very large speed. However, on an astronomical scale, it indeed can take light a long time to travel from one star to another. One example is it takes about 4 years from light from our star to travel to the nearest star. Because of this, we often measure astronomical distances in light years, and 1 light year is the distance that light will travel in a year. To give you some better idea of these distances, it takes about 8 minutes for light to travel from the Sun and reach the Earth. Light from the Andromeda Galaxy, which is the nearest large galaxy to our galaxy, the Milky Way, takes about 2 million years to reach us. This means that when we see the Andromeda Galaxy in the night sky, we are actually seeing the galaxy as it was 2 million years ago. On the right, we have a Hubble Deep Field image, and this was able to image the most distant galaxies, and these are about 13 billion light years away. That is what we see now is the galaxies as they were 13 billion years ago. Just as for sound wave, the Doppler effect applies to electromagnetic waves as well. The Doppler effect means that the frequency of a wave will change if the source of the wave is either moving away or towards the observer of the wave. The new frequency is given by the frequency of the emitted wave times 1 plus or minus the speed of the source of the emitted wave divided by the speed of light. If the source of the wave is moving away from the observer, we use a minus. If the source is moving towards the observer, we use a plus. That means that the frequency will increase from a source that is moving towards an observer, and it will decrease as the source moves away from an observer. When we look at objects in the sky, it turns out that all of these are moving away from us, and this means that the black lines in the electromagnetic spectrum that they emit are shifted. They are shifted to lower frequencies, which corresponds to the red colour, and we refer this to the shift as the redshift. Because all electromagnetic waves have the same speed in the vacuum, the relationship between the wavelength and frequency is very simple. The speed of the electromagnetic wave, which is c, which is a constant, is equal to the frequency of the wave times the wavelength of the wave. The full range of frequencies is known as the electromagnetic spectrum, and in the next slides we will discuss the uses of these different types of electromagnetic waves. Radio waves have the lowest frequency in the spectrum, and these are used to broadcast radio and television signals that are received by antennas. They have a frequency range of 10 to the 6 to 10 to the 9 Hertz, and because they have the smallest frequencies, they have the largest wavelengths. Microwaves, these have a higher frequency than radio waves. We use these for cooking and telecommunications and things like Wi-Fi. These have a frequency range from 10 to the 9 to 10 to the 12 Hertz and have wavelengths of 1 millimeter to 30 centimeters. Infrared waves have a higher frequency, and these are used to transfer heat. Remote controls will also use infrared radiation, and the frequencies of infrared radiation range from 10 to the 12 to 4.3 by 10 to the 14 Hertz. On the bottom we have some pictures from infrared cameras which essentially show the heat dissipated from a cat on the left, and on the right we have East Asia. We can see Thailand, Japan and China, and we can see how these things dissipate heat. As one gets further south, more heat is dissipated, and these are shown by the red regions. The pink and blue regions correspond to places further north, and these are the cooler regions. Moving on to electromagnetic waves with even higher frequencies, visible light, which are the type of electromagnetic waves our eyes can detect, has a rather narrow frequency range. It starts off at 4.3 by 10 to the 14 Hertz, which corresponds to the red colour, and goes to about 7.5 by 10 to the 14 Hertz, which corresponds to the violet colour. Ultraviolet light has a higher frequency still. This causes tanning, but can also cause burning of the skin when exposed to the sun and skin cancer. Some insects can actually see in ultraviolet light, and some flowers have some markings that are only visible under ultraviolet light. Going to higher frequencies still, X-rays, these have frequencies from 10 to the 14 to 10 to the 20 Hertz, and as we all know, they are used for medical imaging. X-rays can penetrate soft flesh, but they can't penetrate hard materials such as bone. So if X-rays are exposed to a body, an X-ray camera at the back can see the differences between bone and soft flesh and see if there's anything wrong with the bone in the process. Gamma rays have the highest frequencies, which correspond to frequencies of 10 to the 20 Hertz or more. They are extremely energetic and usually produced in nuclear reactions, which we will see when we move on to chapter 32. They are also destructive to living cells. In this example, we show how they can be used to sterilize food. On the left, there are some strawberries covered with mold. The mold is something that's living, and the strawberries themselves can then be exposed to gamma rays, and the gamma rays will kill all the mold and give us the strawberries on the right. They are also used in cancer treatments to destroy cancer cells. As shown in the previous chapters, the energy density due to an electric field, which we refer to as UE, is half times epsilon zero times the value of the electric field squared. For a magnetic field, this is equal to 1 over 2 times mu naught times the value of the magnetic field squared. Therefore, the total energy density in an electromagnetic wave will come from the electric field and the magnetic field, and this will equal half epsilon zero E squared plus 1 over 2 mu zero B squared. It can actually be shown that the energy density from the electric contribution is the same as the energy density from the magnetic contribution. If we write the average energy density, and we're interested in an average because the electric and magnetic fields are varying, this average energy density will be half epsilon zero times the RMS of the electric field squared plus 1 over 2 mu zero times the RMS of the magnetic field squared. Again, assuming these two terms are equal, we can more simply write the average energy density as epsilon zero times the RMS of the electric field squared, or as 1 over mu zero times the RMS of the magnetic field squared. If we make these contributions equal, so we say that the electric field energy density is the same as the magnetic field energy density, we can actually rewrite the electric field as 1 over square root epsilon zero times mu zero times by the B field. As we know, this 1 over square root epsilon zero mu zero is simply the speed of light, so we can write the electric field as the speed of light times the magnetic field. Intensity is defined as the amount of energy something receives divided by the area in which that energy is received over and the time at which it takes to receive that energy. If we think of an electromagnetic wave, we can think of the wave delivering a volume to a particular area. That volume will equal the area times the speed of light times the time. Then if we times by the energy density, we get the amount of energy that's delivered to the area. That is then divided by the area times the time, and we find that the areas and the times will cancel. So the intensity of an electromagnetic wave is simply the energy density of the wave times by the speed of light. Now, if we take the previous expressions for energy density, which we determined on slide 18, one can show that the intensity is either equal to the speed of light times epsilon zero times the E field squared, or the speed of light divided by mu zero times the B field squared. An electromagnetic wave will also carry momentum, and that momentum is equal to the energy of the wave divided by the speed of light. We can observe the effects of the momentum in electromagnetic waves in the form of radiation pressure. The pressure will equal the average intensity divided by the speed of light, and in this example we see a comet approaching the Sun. The reason the comet has a tail is because the radiation pressure pushes gases and liquids off the comet away from the direction of travel. The final topic of this chapter will be on polarization. Polarization simply refers to the direction of oscillation of the electric field. We have an example here where the electric field is oscillating in the z direction, so we say that the polarization direction is in the z direction. This gives us an angle between the electric field and y-axis of 90 degrees. We can then rotate the polarization direction by 30 degrees. This will then give us a polarization direction that is different, and its angle with respect to the y-axis will not be 90 degrees, it will now be 60 degrees since we rotated the polarization direction by 30 degrees. Now, when we refer to light as polarized, we simply mean that the electric fields all oscillate in the same direction. Light that is unpolarized has electric fields that oscillate in lots of different directions, as we see in the diagram on the bottom right. The purpose of a polarizer is to take unpolarized light and polarize it after it passes through it. It works in a way that we can understand using a mechanical analog. Here we have some string that we oscillate up and down, and the wave that's produced on this string can pass through the vertical slit rather easily. If we then rotate this vertical slit by 90 degrees, so it's horizontal, if we then have a string that's oscillating vertically, then the wave at the horizontal slit will cease to exist. A polarizer with light operates on the same principle. Now, when polarized light travels through a polarizer, there will be a component in the direction of the polarizer that will be transmitted. The component relates to the electric field, so the electric field that survives will be cos theta times smaller. Since the intensity is proportional to the electric field squared, that means that the intensity that survives will be cos squared theta smaller. This reduction in the electric field gives us the law of Malus, which tells us that the transmitted intensity will be equal to the original intensity, I0, times by cos squared theta, where theta is the change in the direction of polarization. We can see that when theta is 0, the full intensity will transmit, and when theta is 90 degrees, then none of the intensity would transmit, as cos squared theta will be 0. The light exiting from the polarizer will be polarized in the direction of the polarizer with this reduced intensity. When an unpolarized beam passes through a polarizer, the intensity reduction is a factor of 2. That is to say that the transmitted intensity is half the original intensity. The light that leaves the polarizer again will have a polarization direction which is the same as the polarizer direction. In this situation, we have unpolarized light that passes through a polarizer. Its intensity will be reduced by a factor of 2, and then it will pass through another polarizer which will change its direction by theta. The reduction in intensity from this will be cos squared theta, and the final intensity will equal half the original intensity times by cos squared theta. Unpolarized light can be partially or completely polarized by scattering from atoms or molecules. Here we have an example where unpolarized light hits a molecule. The light that is scattered to point A is still unpolarized. We have light that scatters to point C, which is partially polarized, and by partially polarized we can see that some of the horizontal oscillations have been reduced. The light that scatters to point B is completely polarized, and in this case the only direction of oscillation is in the vertical direction and there are no oscillations in the horizontal direction. One example of this process is light that travels through the atmosphere at sunset. The atmosphere contains molecules, and these molecules can act in a way to polarize the light, as we discussed in the previous slide. In this case, the light travels horizontally. The person on the hill will observe light that is unpolarized, and the person at 90 degrees to the original direction of the light will receive polarized light where the oscillation is only in one direction. Polarization can also occur when light is reflected from the molecules in the water. Here the light hits the water and a component will be scattered at 90 degrees with respect to the original direction, and this component is indeed polarized as the person on the beach observes. There are a number of uses of polarization. Perhaps the most obvious is sunglasses. These polarize light in order to reduce the intensity so we can see better in bright conditions. LCD TVs use polarizers to vary the brightness based on the same principle. They are used in viewing 3D movies, photography. In the above picture, a polarization filter is attached in front of the lens, and this gives a nicer view of the sky. They are used for satellite communication, and they can be used for navigation.